Today we have an integration technique which lets us get a handle on all rational functions of polynomials. This is section 7.4 and it's on partial fraction decomposition. And the driving idea behind this is that even in fractions, what you have is generally a sum of some simpler parts. For example, if I had the fraction 7 over 12, I might want to decompose this into fractions with prime denominators. 2 and 3 are the prime components of 12, and so I'll have smaller, simpler fractions which add together to give me the total of 7 over 12. But we'll soon see with this example that those pieces aren't quite enough, because no matter what I choose for here, I have for A, let's see, if I try to find a common denominator between these two, I'm going to get 3A over 6 plus 2b over 6. And what I'm going to have is that, well, 3a plus 2b is only going to give me multiples of 2 as over 12. So let's see, 7 over 12 equals 2 times 3a plus 2b over 12. Which is equal to 6a plus 4b over 12. But this doesn't work because this only gives me the even numbers. 6 and 4, those are always even. So regardless of what a and b are, this decomposition that I thought I had is only going to give me even multiples and fractions of 12. So what we actually need out of this is an extra refinement. We need a c over 4. We'll need prime powers as components for our problems. So let's try this again, adding 4 into the mix. I had a over 2 plus b over 3 plus c over 4. Because maybe I have an extra quarter thrown into there, which is a smaller piece than the 1/2 could have given me. Well, if I find a common denominator now, I'm going to need to use a common denominator of 12. So I'll have 6a plus 8b plus 3c all over 12. Sorry, that's not an 8b. This should be a 4b, because 4 times 3 is 12. So some combination of the numbers a, b, and c with the corresponding coefficients is supposed to add up to 12. And if I think about it, if I let a equal to 0, b equal to 1 and c equal to 1, then I'll have 7 over 12 is equal to 0 plus 4 times 1 plus 3 times 1 all over 12, and certainly 4 plus 3 is equal to 7. But in a decomposed form, I had 1/3 plus 1/4. I have the sum of smaller, simpler fractions. Of course, with integers, there's more than one solution, because I could have also done a equal to 1, b equal to 1, and c equal to -1. Then I would have 7 over 12 is equal to 1/2 plus 1/3 minus 1/4. Which, numerically, if we check it, is equivalent, but it's a different decomposition, I suppose. Now the reason we're interested in this is because something like 2x cubed minus 5x squared minus 2x minus 1 all divided by all over x to the 4th plus x squared minus 2. If I had something like that on the inside of an integral, that would be horrible. I mean, I could kind of try to do like a, what is this? Maybe a u substitution, but I've got far too much stuff on top in order to do that successfully, and none of my other techniques are actually going to help me with this problem. However, if I were able to break this fraction up into components which were all over simpler factors of the denominator, like I did with the 12, I would have a much easier time. And the way this decomposition works is like this. Let me factor the denominator here. I saved this ahead of time. The denominator is x squared minus 1 times x squared plus 2. And I can always factor a polynomial into a product of linear factors and irreducible quadratics. So actually, I have x plus 1 times x minus 1 times x squared plus 2. There's my irreducible quadratic. And the rules for this decomposition is going to look like this. This is going to say that 2x cubed minus 5x squared minus 2x minus 1 all over x plus 1 times x minus 1 times x squared plus 2 should be equal to some number over x plus 1 plus some number over x minus 1 plus actually a line all over x squared plus 2. So here I have a decomposition where I've broken the denominator up into its, I guess, prime factor components. But the advantage polynomials have over my whole number example that I did before is the choices for these coefficients are all going to be unique. And there's a lot of advanced algebra reasons that this is all true, but we don't want to get into that. Suffice to say, if I have a part of my problem, then the degree of the top should be smaller than the degree of the bottom for my part. But if we look at the fractions that we have over here in the decomposed version, well, I can already see ahead what is my integral going to look like now. Well, the first one, that's just going to be maybe a slight u substitution, and it's going to end up being a natural log of something. The second one is going to be a slight u substitution, and it's just going to end up being the natural log of something. The third one could be several things. What I would do personally is split off the cx and the d to two separate fractions. So I had cx over x squared plus 2 plus d over x squared plus 2. One of those will be u substitution, and the other one is going to turn into some multiple of arctangent. So without even doing a whole bunch of work, I already know what my integrals are going to look like at the end of this problem, even though I had something, you know, totally random practically at the beginning. So let's proceed with this. The original rational expression is supposed to be equal to the decomposed version. So what we'd like to do is solve for each of these variables. So let's do that. Let's say we have I'll have a times x minus 1 times x squared plus 2 plus b times x plus 1 times x squared plus 2 plus cx plus d times x plus 1 times x minus 1. And this is all over the common denominator, which was x plus 1, x minus 1, x squared plus 2. This would be the same thing as if I had taken the denominator that I had over here on the left-hand side and multiplied it to both sides. Because what's going to happen now is that my 2x cubed minus 5x squared minus 2x minus 1 will be equal to the numerator I have over here. A times x minus 1 times x squared plus 2 plus b times x plus 1 times x squared plus 2 plus cx plus d times x plus 1 times x minus 1. Then what I would have to do is multiply all this out and then compare coefficients to try to solve for a, b, c, and d. So I'll do that. I have a times x cubed plus, well, minus x squared plus 2x minus 2 plus b times x cubed plus x squared plus 2x plus 2 plus cx plus d times x squared minus 1. Several steps. Let's distribute these coefficients. I'll have ax cubed minus ax squared plus 2ax minus 2a plus bx cubed plus bx squared plus 2bx plus 2b. Alright. Plus cx cubed plus dx squared minus cx minus d. And this big whole thing is supposed to equal 2x cubed minus 5x squared minus 2x minus 1. So I'm going to collect all of my like terms together. I have a plus b plus c times x cubed plus minus a plus b plus d times x squared. Let's try to keep track of these. I did x squared, so that's minus a plus b plus d. Okay, now for the linear, plus 2a plus 2b minus c times x plus 2a plus 2b minus c. And then we're left with minus 2a plus 2b minus c for the constant term. So we got rid of all of our parts. So this gives me a system of equations. I have a plus b plus c equals 2. I have minus a plus b plus d equals minus 5, because the coefficients, if two polynomials are going to be equal to each other, the coefficients for each term must match up. I have 2a plus 2b minus c is equal to minus 2. And I have minus 2a plus 2b minus c is equal to minus 1. So I've got 4 equations and a total of 4 unknowns. Hold on. My D was supposed to show up twice. I made a copy error. So let's see. The D was supposed to distribute to these guys, which means I'm supposed to have a minus D here, which means this one is supposed to be a minus D. Much better. You do enough of these and you get a good feeling of what's supposed to show up. Now there's lots of ways we could try to do these. One way, which I'm not going to go through extensively, is we could do it with matrices. 1, 1, 1, 0, 2, minus 1, 1, 0, 1, minus 5, 2, 2, minus 1, 0, minus 2, minus 2, 2, 0, minus 1, minus 1. I could row reduce this matrix, whatever that means, and that would give me a solution for A, B, C, and D, which is a one step if you have a calculator handy. Well, let's suppose that we don't. Then I would have to go through and try to solve all of this. All of these are just a little bit different, but I'll notice, let's take this one and this one. This one starts off with a plus b, and this one starts off with 2a plus 2b. So I could solve for a plus b from the first one, and I could find out what c is from the third one. And the process here is just going to be trying to notice stuff like that. In general, you're just going to solve for one variable, plug it into the next equation, solve for a new variable, plug it into the others, until you have enough information to solve for one of the variables, and you work your way back. So I have a plus b equals 2 minus c, which means 2 times a plus b, or 2a plus 2b, would have to be equal to 4 minus 2c. This would be the same thing as multiplying this first equation by 2, and then I'm going to subtract it from this third equation. So if 2a plus 2b is equal to 4 minus 2c, that means 4 minus 2c minus c is equal to minus 2. So 4 minus 3c equals minus 2. I'll subtract 2 and I'll add 2 and I'll add 3c. So I should have 6 equals 3c, so c equals 2. Alright. So if c is equal to 2, I can replace all of the c's in my set of equations up there. So I'll do that. I'll have a plus b plus 2 now is equal to 2. I have minus a plus b plus d is equal to minus 5. Now 2a plus 2b minus 2 is equal to minus 2. This gives us some new information. No, let me finish this. Minus 2a plus 2b minus d equals minus 1. So this gives us some new information. This says that a plus b is equal to 0, which means a is equal to minus b. So I'm going to substitute that into my equations and try to solve for a or b. It's not going to do any good to use the first and third equations again, because I used that to get this new equation, a plus b equals 0. So those are used up already. So I'm going to do it into the second and to the third. A equals minus b. So minus a would equal minus minus b. So I have b plus d equals minus 5. And I also have plus 2b plus 2b minus d is equal to minus 1. So 2b plus d equals minus 5. 4b minus d is equal to minus 1. And from these two equations and two unknowns, I have to solve for b and d. So from the first one, I'm going to subtract 2b from both sides, and that'll give me d equals minus 5 minus 2b. And I'll plug that in up there. So I have 4b minus 5 minus 2b, and that's equal to minus 1, which says, this is going to let me solve for b now, because that's all that's left. 4b plus 5 plus 2b, so that's 6b plus 5 is equal to minus 1. If I subtract 5 from both sides, I have 6b equals minus 6, or b equals minus 1. Alright, and since a was equal to minus b, that means a is equal to positive 1. So all that's left now is d, and I can pick that out of anywhere. So I already have d right up there. If b is equal to minus 1, that means d is equal to minus 5 minus 2 times minus 1, which is plus 2, which is minus 3. I'll box that. Oh. So a is 1, b is minus 1, c is 2, and d is minus 3. So I'll return to my decomposition. Oh, brother. All the way back up here. A equals 1, b equals minus 1, c equals 2, and d equals minus 3. Let me cheat with technology for a little bit. So on my decomposition, for 2x cubed minus 5x squared minus 2x minus 1 all over x plus 1 times x minus 1 times x squared plus 2, that's equal to 1 over x plus 1 plus negative 1 over x minus 1 plus 2x minus 3 over x squared plus 2. And you can check this. You can find a common denominator on the right, multiply it all out, and you'll be good to go. But what we were trying to do with this was integrate it, right? So we have this awful integral on the left, and with a little bit of work, a lot of bit of work, we have this much nicer integral on the right. is equal to the integral of 1 over x plus 1 dx minus the integral of 1 over x minus 1 dx plus, I'm going to split this, 2x over x squared plus 2 dx minus the integral of 3 over x squared plus 2 dx. Now, I've done so many integrals lately. I know that this one is going to be the natural log of the absolute value of x plus 1 plus c. This one is going to be natural log of the absolute value of x minus 1 plus c. This one is going to be a u substitution, where the u is the denominator. So this is just the natural log of x squared plus 2 plus c. Now this last one is going to be 3, if I do either fancy u substitutions or now this last one, if I do some fancy u substitutions or work on it like it's a sum of squares, so I can treat it like a trig substitution problem. Now what I'll get at the end of that is I'll have 3 over the square root of 2 times the arctangent of x over the square root of 2 plus c. Which was a lot easier than I thought it was going to be in the beginning. So I have the natural log of x plus 1 minus the natural log of x minus 1 plus the natural log of x squared plus 2 minus 3 over root 2 arctangent of x over the square root of 2 plus c, a bigger c. Yes. There are some other ways to write this, but this is generally how one of these problems is going to go down. And a lot of the work is going to be trying to solve for the coefficients. But sometimes there is an easier way. And this applies to a lot of them, and it can save us a lot of time trying to get some of the coefficients. But just to not be redundant, I'm going to do a slightly different polynomial. I'm going to have 2x cubed plus 5x squared minus 10x minus 15 divided by x squared minus 1 times x plus 2 quantity squared. What happens is I have a repeated factor down here, so just like the example where I had 12, where I needed that extra refinement of 1 over 4, which is 1 over 2 squared, I'm going to take account of that when I do the decomposition here. Sometimes we need that extra little bit. So the decomposition is going to look like this. I'll have x squared minus 1, that factors, so I'll have a over x plus 1 plus b over x minus 1 plus c over x plus 2 plus the possible refinement of having d over x plus 2 squared, just like I had a c over 2 squared for the 7 over 12 example. But we're going to have a slightly easier way of solving for these coefficients. So after I find a common denominator, I'm going to have a times x minus 1 times x plus 2 squared plus b times x plus 1 times x plus 2 squared plus c times x plus 1 times x minus 1 times x plus 2 plus d times x plus 1 times x minus 1. Now instead of just multiplying everything out, what I'm going to do is I'm going to try to evaluate both these polynomials at a couple of x values. Because if the polynomial on the left is supposed to be equal to the polynomial on the right, then when I plug in a number, they should both give me the same number. But what I'm going to do is I'm going to plug in the roots to each of these little linear factors. So if I plug 1 into the left-hand side, I'm going to have 2 plus 5 minus 10 minus 15. Which looks like I get minus 18. But if I plug 1 into the right-hand side, let's label this x equals 1. If I plug 1 into the right-hand side, I'm going to get a times 1 minus 1, which is 0, plus b times 1 plus 1 times 1 plus 2 quantity squared, plus c times a 1 minus 1, which is 0, plus d times a 1 minus 1, which is 0. And look at that, all I had to do was plug in one number, and I got b already. 18b is equal to negative 18, which means that b is equal to negative 1. Let's plug in x equal to negative 1. On the left-hand side, we'll get 2 times negative 1 cubed, so that's minus 2, plus 5 times 1 squared, minus 10 times negative 1, which is plus 10, minus 15. So those cancel, and I end up with negative 2. If I plug negative 1 onto the right-hand side, I'm going to get a times minus 1 times minus 1 plus 2 quantity squared, plus b times minus 1 plus 1, which is 0, plus c times minus 1 plus 1, which is 0, plus, again, 0. Which means it looks like I got minus 1 plus 2, that's 1, squared is 1, so I have minus 2a is equal to minus 2, which means a is equal to 1. Okay, what's left? X equals 2. No, negative 2. X equals minus 2. On the left, I'll have 2 times minus 2 cubed, which is minus 8, so I'll have minus 16, plus 5 times minus 2 squared, which is 5 times 4, which is 20, plus, minus 10 times minus 2, which is plus 20, minus 15. Which looks like I get 9. Now if I plug minus 2 into the right hand side, I'm going to have a 0 for the a term, a 0 for the b term, a 0 for the c term, and I'll have whatever d is. So I'll have 0 plus 0 plus 0 plus d times minus 2 plus 1 times minus 2 minus 1, which is equal to minus 2 plus 1 is negative 1, minus 2 minus 1 is negative 3, so I have d times minus 1 times minus 3, which is 3d, which means d is equal to 3. So I've found a, I've found B and I've found D. All I'm missing is C. So what I'll need to do is find some way of finding out what C is. Fortunately, I know 3 out of 4 of my coefficients, so I could just choose any other number to evaluate, and on C will be the only number left. So I'm going to choose x equals 0. It's not one of our factors, but since I know A, B, and D, the only coefficient left is C. So I'll be able to solve for what C is. If I plug 0 in on the left, I'll have 0 plus 0 plus 0 minus 15, so I get minus 15. And if I plug 0 in on the right, I'll get minus 4a plus 4b minus 2c minus d, but I know that a is equal to 1, b is equal to minus 1, and d was equal to 3. Which means this is equal to minus 4, minus 4, minus 2c, minus 3, which is minus 11 minus 2c. That's supposed to be equal to 15, no, minus 15, which means minus 2c is equal to minus 4, or c is equal to 2. So I've found my decomposition. And I would go through and just integrate all of those if I was looking for an integral. So to summarize with a bigger example, if I had some polynomial all over x minus a1 to the n1 times x minus a2 to the n2 plus whatever, not plus, times whatever times x squared, yeah sure, x squared plus bx ax squared plus bx plus c to the m1 x squared plus bx plus c to the m1 times, oh, those should have ones, x squared plus b2x plus c2 m2, etc. where the degree of p of x is less than the degree of the denominator, specifically that is n1 plus n2 plus all those linear factors plus 2m1 plus 2m2 plus 2 times all those quadratic, irreducible quadratic factors. Then there's the decomposition. Which is equal to, let's see, I'll have a over x minus a1 plus, sorry, a1 over x minus a1 plus a2 over x minus a2 a sub 1 comma 1 over x minus a1 plus a sub 1 comma 2 over x minus a1 squared plus a sub 1 comma n1 over x minus a1 to the n1 plus a sub 2 comma 1 over x minus a2 plus a sub 2 comma 2 over x minus a2 squared plus dot 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 a sub 2 comma n2 over x minus a2 to the n sub 2 plus dot dot dot, we don't want to go that far, plus b 1 comma 1 x plus c 1 comma 1 all over x squared plus b1x plus c1 plus b1 comma 2 x plus c1 comma 2 plus dot dot dot. Oh boy. Plus dot dot dot. Looks awful. Specific general example. Let's suppose I had some polynomial divided by x cubed times x squared minus 1 times x squared plus 2 times x squared plus 1 quantity squared. Which of course factors a little bit more, right? Because I have p of x over x cubed times x plus 1 times x minus 1 times x squared plus 2, that's an irreducible quadratic, times x squared plus 1 squared, that's an irreducible quadratic. Then according to the decomposition rules, I've got 3 regular x's So this should be equal to a over x plus b over x squared plus c over x cubed plus d over x plus 1 plus e over x minus 1 plus fx plus g over x squared plus 2 plus hx plus I over x squared plus 1, and that's repeated, so I'll also have a jx plus k over x squared plus 1 quantity squared. And whatever p of x was, then I would have to go through and solve for all of those coefficients. But in an example that big, you might as well use a computer or calculator and do it with linear algebra, the row reduction in the matrix thing. So, there are two additional notes to make for this section. One, if the polynomial on the top of the fraction is bigger than the polynomial on the bottom of the fraction, or partial fraction decomposition requires the top to have a smaller degree. So if it's equal to, if the degrees are equal, or if the degree on top is bigger, you would have to do long division. So if I had a problem which looked like x cubed minus 4x minus 10 over x squared minus x minus 6, this bottom factors as x minus 3 times x plus 2. So this would have to be equal to a over x minus 3 plus b over x plus 2. But when I find a common denominator, I only have ax plus 2a plus bx minus 3b all over x minus 3 times x plus 2, which is a plus b x plus 2a minus 3b. These can't possibly be equal to each other because on the left I have a cubic term and on the right I only go up to the linear term. So I'd have to do long division first. I have to take my x cubed plus 0x squared minus 4x minus 10 and divide it by x squared minus x minus 6. To get that x cubed minus 4x minus 10 all over x squared minus x minus 6 is equal to x plus 1 plus 3x minus 4 all over x squared minus x minus 6. And I can use partial fraction decomposition on that part. In this first part, if I needed to integrate it, I can integrate that just fine. 2, depending on the irreducible quadratic you end up with, you may need to use complete the square in order to perform the integral. So for example, if I had 3x squared minus 3x plus 12 all over x cubed minus 6x squared plus 12x. I could factor an x out of the denominator here. And I have a quadratic left. But if I check with the quadratic formula, I'll see that this quadratic is an irreducible quadratic. So I'll do this final decomposition just so that we can see what the end results are going to look like if we try to integrate it at this function. If I needed to integrate this first part, I would just have natural log of x. But what would I do about the second part? A simple u substitution doesn't seem like it's going to do it. Well, the answer is to complete the square on it. Because if I complete the square, let's see, I'll have, this is minus 3 times 2, so this should be plus 9 minus 9. So I'll have x squared minus 6x plus 9 minus 9 plus 12, giving me here x minus 3 quantity squared plus 3, allowing me to rewrite my problem like so. And on here, I would have to do maybe a u substitution first before splitting it up into the two parts where one version is an extra u substitution and the next version is an arctangent problem. So as you've seen, these problems can end up being very long, but they're really kind of the only way to deal with a large class of functions, rational functions of polynomials. Next time we'll have a strategy of integration, which is some tips on approaching integrals in the wild and what to choose over what when you're not sure what to do.